Hello, my name is Thibaut Bagné-Rasroux, and today I'm going to present you a paper named Qualitative Evaluation of Language Model Rescoring in Automatic Speech Recognition. This work was done with the collaboration of the LS2N, the LIA, and the LIUM. In ISR, the way a system works is that you have a speech and the automatic system will do a transcription that we often call the hypothesis. The reference is the transcription done by a human to compare the two texts. In ASR, the most commonly used metric is the word error rate, which is the sum of the substitution, the insertion, and deletion divided by the number of words in the reference. So for example, for the reference we learn maths for fun, if the hypothesis done by the system is we burned the math 4, you have 4 mistakes, 2 substitution, 1 insertion, and 1 deletion. The problem with this metric is that every substitution has the same weights. For example, learn and burn, which is a bad error for us and for application, are considered the same way as math and math without an S. What do we want to do with this work? The objective is to study the impact of a linguistic rescoring on different aspects, such as the grammar, the semantics, words character, and the quality for downstream tasks. We would like to highlight the need for a metric closer to human perception and change the way how we evaluate ISR systems. So our plan is to take a look at the use metric. I will present the ISR system that we evaluate. We will take a look at the result and draw some conclusion. And finally, I will show you our ideas for any future work. All metrics are divided in 3 categories. As you can see, there are the lexical, the grammatical, and the semantic categories. The lexical categories has the purpose to evaluate words and the characters, while the grammatical is supposed to evaluate things as the part speech and the lemmas. The semantic metric are expected to evaluate the meaning of the sentence or the words, and it will use embeddings. So the word error rate and the character error rate are basically just the Levenstein distance on words for the word error rate and on character for the character error rate. The part of speech error rate is evaluation metric that use parts of speech. So here, for example, we can have a part of speech tag with our tagger. And for here we have pronoun, verb, math, etc. And we will apply a word error rate on the part of speech. So here we can see that the math and math share the same none. So this will not be considered as an error. And here for learn and burn, they share also the same part of speech, but here this will be a problem for this metric, as learn and burn do not have the same meaning at all. We could use a universal part of speech or an extended French version. This extended French version has the particularity to have a higher granularity. For example, NMS is singular masculine noun, and you can have also plural masculine noun, feminine noun, etc., instead of just one part of speech for all nouns. Therefore, we could use 2 variants of this metric, aka the detailed part of speech error rate and the universal part of speech error rate. The lemma error rate is close to the part of speech error rate, but it works on lemmas. So we use a French lemmatizer from Spacey, and we obtain our or lemmas. And here, for example, learn and burn do not have the same lemmas, while maths and math have the same lemma, and they will not be considered as an error. A variant of this metric is the lemma character error rate, which is just a character error rate applied on the lemmas. The idea behind the embedding-based metric is that embedding are expected to represent semantics. The main idea is that if the reference and the hypothesis are different, but the embeddings are close in the embedding space, the error is expected to be less severe. For example, we have the embedding error rates, which is a word error rate weighted by the semantic distance of the substitutions. So here, for example, for math and maths, we will compute a cosine similarity between the embedding of the word math and the embedding of the word math without an S. And if the words are close in the semantic space, we will consider as a small error with 0.1 instead of 1, like for learn and burn. The semantic distance is the cosine similarity between the reference and hypothesis sentence birth projection. The idea is that for the reference and the hypothesis, we project them with the sentence birth embeddings, and we compute the cosine similarity between those two embeddings. If the embedding are close, the score will be close to 1, and if the meaning are far, the score is expected to be close to -1. The BERT score is a metric that was at first developed for automatic translation. It consists in computing a score given the maximum similarity between each token from the reference and each token from the hypothesis. What does that mean is that, for example, for imported, we will compute a similarity score between imported and people, imported and enjoy, imported and driving, imported foreign, imported in cars. And we will choose the word with the highest score. So here, apparently, it's foreign. And as high is the similarity between those words, the higher will be the BERT score. Here, the higher is the maximum similarity, the better is the score. This metric is useful because it allows to overcome word order that might be disturbed by deletion in insertion. So now we will take a short look at the ISR system. Our system is based on a Caldi recipe. It has a neuronal acoustic model based on a TD&NF architecture. It uses an optional rescoring using a language model, aka the RNNLM and a quadrigram. It is also trained on 940 hours of French audio from the radio and television broadcast. So now let's take a look at the results. We will take a look at the overall impact of the rescoring and the local impact, and then we will see the intermetrics correlation. So here, to read this tab, you have the all of metric and two different scores for our two systems: the system without the rescoring and the system with the rescoring. The reduction is the relative gain due to the rescoring. And we can see that the rescoring improved the performance for all metrics. The SEMDIST and the BERT score metric have the lowest relative gain with -9 and -8.1. The rescoring does not improve the semantic aspect as much as the grammatical and lexical level. And we can see that the words that are already semantically close are better predicted when the rescoring is applied. About the local impact of the rescoring, 50% of the sentence prediction are better with rescoring. 37% of the sentence are worse with the rescoring. And for the rest, they are the same with or without rescoring. We ask ourselves why some sentences are worse when the rescoring is applied, because it's supposed to make the result better. So we were kind of surprised. We made one hypothesis. It's that the rescoring pushes the prediction toward the written domain instead of the spoken domain. Here is the tab for the intermetrics correlation. It can be read as the 89.34 is the correlation of Pearson correlation between the word error rate and the character error rate. We can see that the character error rate and the lemma character error rate are the same. So if it is not useful to compute the lemma if you just can do a character error rate. The same list correlate the list with the others. It means that if we want a better performance on downstream task, it is not always useful to focus on minimizing the word error rate, because it might not correlate strongly with better performance. If we use sentence embeddings, of course. The embedding error rate is correlating with the word error rate, but it is also the metric that correlates best with the semantic distance and the BERT score. That means that it has the faculty to correlate with lexical category and semantic category, which made this metric a hybrid metric. The lemma error rate correlates the best with the universal part-of-speech error rate, and it has also a better correlation with the detailed part-of-speech compared to the lemma character error rate. Then we can take a look at our future work. In the future, we would like to evaluate our other system. We are thinking about evaluating an end-to-end system, or also a hybrid version, which uses ways-to-wake inputs. We'd like to develop a new metric closer to human perception, because when we speak, we are able to understand even when there are noise or mistakes done by the human. That would be interesting to observe why we are able to understand it. We also like to conduct perceptual experiments of the error done by automatic speech system, because it would be useful to study the correlation between metrics and human perception, and it might help to choose a metric and choose a system if we want the transcription to be read by humans. And also an idea of future work is to find an explanation for the drop in local performance of specific sentence. Like, we don't really know why they don't work well, and that would be interesting to study the reason. Thank you for your attention. As this is a video, if you have any question, feel free to send me, ask any at my mail address. Thank you.